Hey everyone, so today we are going to talk about vector space, one of the first abstract space that you study once you come to an engineering or a bachelor programs. So what is a vector space? Well, if I want to say this in a very simple term, it's a set, or I would say it's a very nice set. Now set you have already studied, right? So what is a set? It's a collection of distinct objects. Like the sets which you have seen are natural numbers, whole numbers, rational numbers, integers, irrational numbers, real numbers, complex numbers. These are the standard set of numbers. You have also seen matrices. Like if I take all 2 cross 2 matrices and I keep on changing ABCD, then this is also a collection of sets. I can take collection of all polynomials. Say I can take collection of all degree 2 polynomials where a0, a1, a2 are real numbers. So these are all the types of sets. Or you can take collection of all sequences, you can take collection of all functions. So among these sets, some of them are nice sets. Nice sets as in what? The sets that satisfy some 9 properties, then such a sets are called as a vector space. Okay, so vector space is nothing but it's a set only, but then it's a nice set. Nice set as in the set which satisfies 9 properties. I'm going to state those 9 properties, and while stating I will be also telling you an example. Okay, so I will state a property, I will take an example. So I will do this simultaneously so that you will understand the properties clearly. So today I am only going to do one example along with the definition, and in the next lecture I will take some more examples. Okay, so I gave you a brief idea. So it's a nice world which satisfies 9 properties. Now what are those 9 properties? Now for those 9 properties we will need some operations. Okay, so to be precise, here we will need 2 operations. Now what are those 2 operations? Those 2 operations are vector addition and scalar multiplication. Now what do you mean by vector addition? Okay, first of all we will denote a vector space by V. Okay, so capital V is a set, and on this set I am going to define 2 operations. One is called as a vector addition. Why vector addition? Because I will call, if V is an element of the set V, then instead of calling this as an element I will call this as a vector. Okay, so V bar. So elements of vector space are called as vectors. Okay, so first operation I will define is called as a vector addition. That means what? You have a set with you, you take 2 vectors from the set, you add them up, and then the addition should also fall under the same set. Okay, so what is my plus operation? It will take 2 vectors, say v1 and v2. v1 and v2 are the vectors from the vector space V or from the set V, and you add them up. What you do is you add them up, then the addition should also be an element of V. Okay, so another way of writing this is plus this operator, or this is a function which will take 2 vectors. So plus is from V cross V, because it is taking 2 vectors, so from V cross V, and the output should also be in the set V. Okay, so that's why this is the thing you usually see. V is a set with plus operation, and you will see V cross V to V. V cross V, why? Because we are taking 2 vectors and the resultant should also be an element of V. So this is what my vector addition is. So you take 2 vectors, you add them up, the addition should fall into the set V. Then we call it is closed under addition. Okay, when this property is satisfied, we say it is closed under addition. The second property is the scalar multiplication. That means what? You multiply your vector, you take a vector, say V bar, and you multiply it with some number. Now which number you should take? One can take real numbers, one can take complex numbers, one can take rational numbers. Can one take integers? No. Well, to define this multiplication, vector space, so this scalar it can be a real number, it can be a complex number, it can be a rational number. Okay, or in general there is a concept of field, arbitrary field. Okay, so if you don't know the concept of field, it is okay, not a worry. You can always think of real number or complex number. Okay, but it can't be an integer or a natural number or whole number, because these sets do not have a structure of field, or they do not have a field structure. Okay, so you can, as if now for simplicity, you can concentrate with real numbers. Okay, you can ignore this for simplicity, I'm saying, but it can be anything. Okay, so vector space is always defined over real numbers or complex numbers or rational numbers. Okay, why we need that? Because for the scalar operation we will need those things. Now scalar means what? You have to multiply your vector by a number. So alpha is the number. So let me take this to be a real number. So r cross v, that means you take a scalar. Now we will call the number to be a scalar. So you take a scalar, you take a vector. The multiplication should again fall into the vector set v. Okay, so you have a vector space, you have collection of real numbers. You take a vector, you take a number, real number, you multiply. This multiplication should also fall into the same set. If the multiplication is falling outside the set, then it is not closed under scalar multiplication. Okay, so what is the scalar multiplication property? You take a real number, you take a vector, you multiply. The product should be in the vector space V. Or you take, if you are talking over complex number, you take a complex number, you take a vector, multiply, it should belongs to V. Okay, so this is what you called as a closed under scalar multiplication. So therefore, as a standard, whenever you open any book and whenever you start reading the definition, they will say consider V plus dot, this triplet. So V is the set, plus is the addition operation that you are defining on the set V, dot is the scalar multiplication operation you are defining on V. Okay, and then you have to mention what is that operation. So plus is from V cross V to V and dot is from R cross V to V. If you are taking R, the scalars from real numbers. If you are taking scalars from complex, you will write C. If you are taking scalars from rational numbers, you will write C. You will write Q. Or if you are taking it from arbitrary field F, you write it as F. But it's okay, we can stop over here as if now. So you have a set with these two operations defined. So it should be closed under vector addition, closed under scalar multiplication. Other than these two properties, there are 7 more properties your set should satisfy so that it will be eligible to be called as a vector space. Now what are other 7 properties? Let us try to see that with the help of an example. Now let us try to see those properties. So V is a set with plus and dot operation. What is the first property? As I said, let me recall once again. You take any two vectors for any V1, V2 in V. What do we want? The addition should also be an element of V. Okay. Now let me take a set for your reference. Let me take R2 as a set. R2 everyone knows, real number comma real number. It's a two-dimensional space, x-axis and y-axis. Right? So this is my V now. So let me take two vectors from this set. So let me take V1. Now how does an element of R2 looks like? You take any number. So this is say 2, 1, 5, 7, minus 2, minus 1. In short, real number, real number. So how my V1 will look like? It will be some real number and real number. In vector space, we always denote a vector as a column vectors. Okay, you never write row wise. It's a standard practice to write column wise. And you take another vector V2. How this V2 will look like? Say some C, D. So your V1 and V2 both are the elements of R2. I am defining addition. How I am defining the addition? You add component wise. So you add A plus C and you add B plus D. So whenever you have a set, the first thing is you should define the vector addition. And this is the standard vector addition that we have always seen in your junior college. So this is the vector addition we have defined. Now is this under this addition operation, is the set closed? Yes. Why? Because if I am taking any two vectors from R2, the addition is again in R2 because A and C are real numbers, so addition is a real number. B and D are real numbers, so B plus D is also a real number. So this is an element of R2. So under this operation, your R2 is closed under addition. Okay, what about the second one? What is the second property? So this is called as a closure property. The second property is associative property. What is associative property? You take any three vectors, let v1, v2, v3, these are any three vectors in the vector space V. Associative says if I add v1 and v2 and then I add v3, that is same as you first add v2, v3 and then you add v1 to it. That means what? You add the vectors in any order, it does not matter, you always get the same answer. That's why we never write the brackets. This property is called as associative property. Adding this two, then adding the third is same as you add second, third and then you add the first. Okay, so if I want to add three vectors, I will write v1, v2, v3 simply, and you can add in any order you want. You always get the same answer. Let us try to see the same thing over here. So my v1 and v2 are this. Let me take v3 as a, b, c, d, e, f. These are the three vectors in R2. Okay, let us try to verify this property for R2. What is my left hand side? I am first adding v1 plus v2 and then I have to add v3. Now what is v1 plus v2? I have already written here. It is a plus c and here it is b plus d. And here I want to add v3. What is v3? It is ef. So and what is this addition? You can see it is a plus c plus e, b plus d plus f. Right? Now let us try to find my right hand side. If you try to find the right hand side, will you get the same answer? Let us try to see that. So what is right hand side? v1 plus v2 plus v3. What is v1? It is ab. What is v2 plus v3? What is v2 plus v3? It is c plus e and d plus f. And now you add this two. What is this? This is a plus c plus e, b plus d plus f. So you can see your left hand side is equal to the right hand side. So your R2 satisfies the associative property with respect to this addition operation. So now let's go for the third operation. The third is called as additive identity. So in your set V, you take any vector. There should exist a unique element 0 bar such that when I add v bar to that unique vector, or I will say the identity element 0 bar, I should get the same answer. If such an element exists, we call that element to be the additive identity. Okay, now in R2, does such an element exist? Does 0 bar exist? Answer is yes. You take 0 bar to be the 0 vector. Then you take any v bar, say AB in R2. What is v bar plus 0 bar? Will you again get the same answer? Answer is yes. What is the answer? AB plus 0 vector. What is the addition? You do component wise. A plus 0 is A, B plus 0 is B. So v bar plus 0 bar is again v bar. And this is true for any vector. You take any vector 1, 2, 3, 4, 100, 2000, minus 1000, 1 crore. You take any vector in R2 and you add it to 0 vector, you always get the same answer. Therefore, the additive identity do exist in R2. Additive identity do exist in R2. So for third property, this is the third property and that is also get satisfied by R2. Okay, let's go for the next property. The next property is called as additive inverse. The next property is called as your set should satisfy additive inverse property. That means what? For any V belongs to V, for this V, there exists some U bar such that their addition should be the additive identity, the 0 vector. For every vector, there should exist U bar such that this should be 0. In earlier case, that 0 bar should work for every V. Here, for every V bar, you should have different U bar. It's okay. So, does that exist here? Yes. In R2, this property is satisfied. How it is satisfied? You take V bar is as AB. This is an element of R2. What should be your U bar so that the addition becomes 0? When you add V bar plus U bar, it should be 0. Obvious, if I want to make their addition 0, I will take minus A minus B. Is this an element of R2? Yes, because A is a real number, so minus A is a real number. B is a real number, so minus B is a real number. So if A comma B is in R2, minus A minus B is also in R2. So what is the addition? When I add A minus A is 0, B minus B is 0, which is nothing but my 0 vector. So for every element in R2, I can always construct U bar such that their addition is the 0 vector. Okay, so this is another property that R2 satisfies. Okay, now the last property with respect to addition is called as the commutative operation. This is the last, fifth property is the last property with respect to addition. We have still not seen the properties for scalar multiplication. Okay, so for addition, the last is the commutativity. That means what? You add the vectors in any order. Means you add first V1 plus V2 or you add V2 plus V1, you should always get the same answer. That means they commute. Okay, and this is true in R2. Why? Because if I take V1 as AB and V2 as CD, what is the addition? We have already seen it is A plus C and B plus D. But these are real numbers. If you add two real numbers, 2 plus 3 or 3 plus 2, you always get the same answer. So A plus C is same as C plus A, B plus D is same as D plus B. Again, what is this? This is CD plus AB. But what is CD? My CD is V2 and my AB is V1. So V1 plus V2 is same as V2 plus V1. So in R2, you add the two vectors in any order. You first add AB, CD and then you add CD, AB, you get the same answer. So we have seen that R2 is satisfying the first 5 properties for a set to be a vector space. What are the first 5 properties? The first one was the closure. If you take two vectors, their addition should again fall into the same set. What was the second? Associativity. You take 3 vectors, V1, V2, V3. You do V1 plus V2 and then you add V3, or you do V2 plus V3 and then you add V1. I am not saying that it should fall into the set again. What I am saying, the answer should be the same. Okay, ultimately they will fall into the set because of the first property, but okay, I want the same addition. Okay, third was the additive identity. For every vector in V bar, there exists a unique, for all these vectors, there should exist a unique 0 bar such that V plus 0 bar is equal to V bar. Then if such a 0 bar exists, we say that 0 bar is the additive identity. Then the fourth was additive inverse. You take V bar, there should exist a U bar, their addition is 0 bar. You take another V bar, there should exist another 0 bar such that the addition is 0 bar. And the fifth property is commutativity. Order does not matter. You add two vectors in any order, you get the same answer. So these were the property for addition. Now there are 4 properties for scalar multiplication. Let us try to understand those 4 properties. Now what is the 6th property? The 6th is called as a scalar multiplication. That means what? You take a vector and multiply it with a scalar. See, scalar is nothing but a number. Okay, now you are grown up kids, so you don't call alpha in R a number, you call it as a scalar. Okay, or in the world of vector spaces, we call the number to be a scalar. Okay, so you take a vector, you take a scalar, you multiply, it should again be the vector in the same set. Then I will say that it is closed under scalar multiplication. So in R2, so let alpha be a real number and V bar in R2. I need to define this multiplication. How will I define? I am defining this multiplication as you multiply component wise, alpha A, alpha B. You take alpha inside. So this is how I am defining. One has to define an operation. Okay, then only they can check other properties. For vector addition, we define component wise. For scalar multiplication, we are defining this way. One can define in different ways, but then one has to check. Okay, you can see one of my lecture that R2 need not be a vector space always if I define this operation in a different way. Okay, I will post the link in the description. Do have a look. Now, okay, coming back to this. What is alpha into V bar? It is alpha A, alpha B. Is this an element of R2? Yes. Why? Because alpha is a real number, A is a real number, so product is real number. Alpha is a real number, B is a real number, so product is real number. So this is an element of R2. So R2 under this operation is closed under scalar multiplication. Okay, good. What is the next property? The next property is, the seventh one is called as associative with respect to scalarity. So that means you have a vector V bar, you multiply it with a scalar beta, which is a real number. So you get a vector because this product is a vector because of this property. Now you multiply this vector by another scalar. That is same as you first multiply two real number and multiply it with a vector. You will always get the same answer. Is this true in R2? Yes. What is alpha into beta? Suppose I am taking V bar as AB. What is this? This is beta A and this is beta B. And what is this? This is alpha beta A. What is this? Alpha beta B. But you can take out alpha beta outside, right? Alpha beta. What is left? AB. But what is this? This is alpha beta. And what is this? V bar. So alpha into V bar is same as alpha beta into V bar. So with this property is also satisfied in R2. Okay. Now what is the next property? Next property is called as existence of multiplicative identity. We have seen additive identity 0 bar. The next is the multiplicative identity. That means what? There should exist one in the field, now real number or complex number or rational number, such that 1 into V bar is always V bar. If such an element exists, then we say that the vector space satisfies this property. Okay, so existence of this element is required to check this property. Okay, and if such an element exists, we say that 1 is multiplicative identity. Now in R2, this property is satisfied. You take alpha equal to 1, then what is alpha into V bar? It is 1 into V bar. 1 into, what is this? AB. And what is the product? It is again AB. So this is again AB, which is your V bar. So therefore, this property is also getting satisfied. Okay, so this is the property which is called as existence of multiplicative identity. Okay, and now comes the last one. The last one is called as a distributive property. What is that distributive property? It says you take a scalar alpha, you take a vector u bar plus v bar, then the scalar should distribute over the addition from the left side. So this should be same as alpha into u bar plus alpha into v bar. This is called as the left distributive because you are distributing alpha over addition or scalar multiplication over vector addition. Similarly, there is called as a right distributive law, which is u bar plus v bar into alpha bar is same as u bar dot alpha bar, not alpha bar, sorry, alpha is a scalar, plus v bar dot alpha. So these two properties are called as a distributive properties. So when you so this is called as a scalar is getting distributed over addition. Okay, this is called as a left distributive law, this is called as a right distributive law. So let us try to verify this property over R2. Well, I will try to do this, you try to verify this. Okay, what is alpha into u plus v? Now let me call u bar as AB, v bar as CD. So what will be the addition? We know that addition is A plus C, this is B plus D. Now what is this equal to? This is nothing but you take your alpha inside. So alpha into A plus C and alpha into B plus D. Now you multiply your alpha inside because these are real numbers. So in real numbers this is true. I can multiply. This is alpha A plus alpha C. This is alpha B plus alpha D. Now this is my left hand side. You try to arrive at the right hand side or you try to start with right hand side. What is alpha into u bar? Alpha AB plus alpha into v bar, alpha CD. What is this? This is alpha A, alpha B plus what is this? This is alpha C, alpha D. Now you know how to add two vectors. It is component wise, alpha A plus alpha C, alpha B plus alpha D, which is the same thing. Similarly, you try to prove this property. So we have seen that these are the 9 properties that a set V should satisfy. And if a set V satisfies these 9 properties, then we say such a set V to be a vector space over real numbers. If you are taking a scalar from real number. If you are taking a scalars from complex number, we say that V is a vector space over complex numbers. If you are taking rational numbers, we will say that V is a vector space over rational numbers. That's one thing. Okay. And another thing is, yeah, we have seen that R2 satisfies all these 9 properties. Therefore, we say that R2 is a vector space over real numbers. Okay. Now, let me ask another question. With this operation, will R2 form a vector space over complex numbers? Answer is no, with the same operations. Okay, what were the operations? For addition, AB plus CD was what? You simply add A plus C, B plus D. So first 5 properties is not a problem. Okay, because they deal with the elements of R2 only. When does the scalar will come? For the remaining 4 properties. So now my question is R2 a vector space over complex numbers? That means what? If I take a alpha to be a complex number, if I take a V bar to be an element of R2, will the product which I defined earlier, under this product, is this an element of R2? Answer is no. This should be true for all alpha, right? So if I take alpha to be say I, which is a complex number, if I take V bar as 2, 3, this is an element of R2. What is the product? What is alpha into V bar? It is 2i and 3i. Is this an element of R2? No. For this to be an element of R2, both the elements should be real numbers. Are they real numbers? No. So this element is not an element of R2. So R2 is a vector space over real numbers, but R2 is not a vector space over complex numbers under this operation. So this is all about vector spaces. Now what you do is you try to prove that R3 is a vector space over real numbers. Now what will be the difference? I took V bar as AB and U bar as, or V1 as AB and V2 as CD. What you do is you take V1 as ABC and you take V2 as DEF. What is the addition? A plus D, B plus E, C plus F. And what is alpha into V? It is alpha A, alpha B, alpha C. And do the same thing and try to prove that R3 is a vector space over real numbers. And once you do that, you try to generalize it for Rn. How will an element of Rn will look like? My V bar will be say A1, A2, dot 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 up to An. How my U bar will look like? Say B1, B2 up to Bn. What will be the addition? A1 plus B1, A2 plus B2 up to An plus Bn. And what will be the scalar operation? Alpha into V bar will be alpha A1, alpha A2 up to alpha An. So what we have seen is Rn for n equal to 1, 2, 3, 4, n can be any natural number. Your Rn forms a vector space over real numbers under this standard operations. Whereas under this operation, Rn's are not a vector space over complex numbers. Okay, so this was just a brief introduction about vector space. So try to verify these examples. If you get stuck, you can ask me in the comment section, and in the next set of lectures, I will come up with some more examples. So if you have any doubt, do ask in the comment section. If no doubt, then do not forget to like, share and subscribe. Thank you.